For most people born in prehistory, life could be brutally short. Yet that does not mean the human body was built to die at 30. A low average could be shaped by the many lives lost during infancy and childhood, while some who survived carried healed injuries, worn teeth, and decades of memory into older age. The cold truth is that an average can hide the people who lived far beyond it. So once childhood was survived, how long could a prehistoric human truly live? For a long time, one of the most repeated statements about prehistoric life has been that people rarely lived beyond the age of 30. The number appears simple, and because it is simple, it is easy to remember. It creates a clear picture, a difficult world, a young population, and lives ending before what we now call middle age. Yet the picture is misleading. When researchers estimate a low life expectancy at birth for a population, they are not saying that most adults suddenly died when they reached that age. They are describing an average formed from every recorded or reconstructed death, including the deaths of infants, children, adolescents, and adults. In a community where many children died during their first years, the average could fall sharply, even if some adults continued living for several more decades. Imagine, only as a simple mathematical example, 4 people whose lives ended at 1 year, 4 years, 35 years, and 60 years. Their average age at death would be 25, but no one in that small group actually died at 25. The average would be real, while the life story it seems to suggest would be false. A person who had already reached adulthood would not somehow inherit the average as a prediction. Their remaining chances would depend on the risks faced from that age onward, not on the deaths that had already occurred among the youngest members of the group. This is the first difficulty hidden inside the famous age of 30. The second difficulty is that there was no single prehistoric population. Prehistory includes an immense span of time, many human species, changing climates, and communities living in environments as different as open grasslands, cold northern valleys, tropical forests, coasts, and dry interior regions. Their food supplies, disease pressures, dangers, movement patterns, and social arrangements were not identical. A number estimated from one place or one period cannot safely become the natural age of death for every human who lived before written history. Even evidence from recent or historically observed hunter-gatherer groups must be used with care. Such communities can help researchers study mortality under conditions without modern hospitals, sanitation systems, or industrial food production. But they are not preserved copies of the Paleolithic world. They have their own histories, contacts, epidemics, technologies, and ecological pressures. Their records can offer comparisons, not a direct census of distant ancestors. The fossil and archaeological record creates another problem. The people whose remains survived are only a fraction of those who once lived. Many bodies were never buried in conditions that preserved bone. Others were damaged, scattered, dissolved by soil, disturbed by animals, or lost before discovery. Even when a skeleton is found, estimating the age of an adult at death is not the same as reading a birth certificate. Teeth, joints, bone surfaces, and patterns of wear can provide clues, but those clues become less exact as adulthood advances. This means that the neat statement that prehistoric people died at 30 is not only statistically confused, it also sounds more precise than the surviving evidence allows. Still, correcting the misunderstanding does not mean replacing it with the opposite fantasy. Prehistoric life carried serious risks. Infection, injury, food shortage, childbirth, exposure, and violence could shorten lives at many ages. Modern medicine has transformed survival, especially during infancy, infection, and physical trauma. The error is not in recognizing that death came earlier and more often. The error is in imagining that an average age was an invisible deadline built into the human body. 30 was never a wall that every prehistoric adult approached and then crossed into death. It was often a summary of unequal outcomes, many lives ending very early, some ending during adulthood, and a smaller number continuing into ages that the average alone cannot reveal. Before asking how long prehistoric humans could really live, we must first release the number that has been standing in the way of the question. A population average can describe a group accurately while describing almost no individual within it. This is especially important when we speak about prehistoric mortality because deaths were not spread evenly across the human lifespan. The first years of life carried risks far greater than those faced by a healthy adult. When many infants and young children died, their short lives pulled the average downward. An adult who had already survived those years had passed through one of the most dangerous filters in the population. That did not make the adult safe, but it changed the question. Instead of asking how long people lived from birth, we would need to ask how many additional years someone could expect after reaching 15, 20, 30, or another age. These are different calculations, and they can produce very different answers. A low life expectancy at birth does not mean that adults normally had only a few decades available to them. It means that the complete pattern of death, beginning at birth, produced a low average. Consider two imaginary communities with the same average age at death. In the first, many children die very young, while most surviving adults live into their 40s or 50s. In the second, nearly all children survive, but many adults die in their 20s and 30s. The same average could conceal two completely different human realities. This is why the question of how long prehistoric humans could really live cannot be answered by one average alone. We must know which stage of life we are discussing and which people had already survived the dangers that came before it. Another important distinction is the difference between a common age at death and the maximum age a person could reach. A population may contain many deaths in early childhood, another concentration in young adulthood, and a small number of people who survive much longer. The oldest individuals do not represent the typical experience, but neither should they be erased. Their existence shows what the human body and a particular environment sometimes allowed. At the same time, a few older skeletons cannot prove that long life was common. They show only that it was possible. Prehistoric evidence therefore requires balance. If we focus only on the youngest deaths, adult survival appears shorter than it was. If we focus only on the oldest survivors, harsh conditions appear less important than they were. Both errors begin when a group statistic is treated as a personal destiny. An individual life was shaped by health, nutrition, injury, pregnancy, disease exposure, climate, mobility, and support from other people. Two adults born in the same community could face very different chances of surviving the next 10 years. One might recover from an injury because others shared food during a period of weakness. Another might die from a small wound that became infected. One might live through several difficult winters. Another might encounter a single season of scarcity at the worst possible moment. No average could predict these separate paths with certainty. It could only summarize the outcomes after they had occurred. This distinction also changes how we imagine age in prehistoric communities. A person of 30 may have been young in biological terms, but highly experienced within the group, especially after surviving childhood, physical work, seasonal hunger, and repeated danger. Someone of 40 or 50 may have been uncommon in certain communities without being impossible. Yet even these broad descriptions require caution because the archaeological record is incomplete and the boundaries between adult age categories are often uncertain. The honest approach is not to replace one misleading number with another. It is to recognize that survival was conditional. Birth began one calculation. Reaching later childhood changed it. Reaching adulthood changed it again. Every stage removed some people from the population while leaving others with a new set of chances. Only after following those changing chances can we begin to understand how long a prehistoric human life might continue. The word prehistory sounds like the name of a single distant age, but it covers an immense and uneven span of human existence. It begins before written records and stretches across environments, populations, and species that did not all live in the same way or face the same dangers. Even within the human family, the story includes forms such as Homo erectus, Neanderthals, Denisovans, early Homo sapiens, and other groups known only from limited fossils or genetic traces. Some overlapped in time, some occupied different regions, some survived for hundreds of thousands of years before disappearing. To ask how long humans could live in prehistoric times is therefore not the same as asking for the life expectancy of one village or one century. It is closer to asking how long human beings could live across a changing world that lasted far longer than recorded history. During that span, climates shifted repeatedly. Wet regions became dry. Grasslands expanded or contracted. Glacial periods cooled large parts of the northern hemisphere, while warmer intervals changed plants, animals, coastlines, and migration routes. A community living near a productive shore could have access to food, unlike that available to a group crossing a cold interior. People living in tropical regions faced different parasites, infections, and seasonal pressures from those living in high latitudes. Even groups separated by a few generations could experience sharply different conditions if rainfall failed, animal movements changed, or a familiar landscape became less reliable. These differences mattered for survival at every age. They affected maternal health, childhood nutrition, exposure to disease, the frequency of injury, and the ability of a group to support someone who was weak or recovering. Technology also changed, although not in one smooth movement from simple to advanced. Stone tools varied across regions and periods. The controlled use of fire, clothing, shelter, food processing, hunting methods, and knowledge of local resources could reduce certain risks without removing them. A warm shelter might make one winter more survivable, yet it could not guarantee protection from infection or hunger. Better cutting tools could improve access to food, but they could not create animals where none were present. Human survival was always connected to a particular setting, not to a universal prehistoric condition. Social life may have varied as well. Group size, movement, food sharing, care for children, and assistance given to injured or older people were not preserved in complete detail. Archaeologists can sometimes infer cooperation from healed injuries, repeated occupation sites, food remains, or tools, but they cannot reconstruct every relationship. We should therefore avoid imagining all prehistoric groups as either constantly violent or naturally harmonious. Both pictures are too simple, and either one would distort the question of longevity. The meaning of age also changed according to the population being studied. A 40-year-old Homo erectus, living more than 1 million years ago, cannot automatically be compared with a 40-year-old Homo sapiens living near the end of the Stone Age. Their bodies, growth patterns, environments, and social worlds were not identical. Even among Homo sapiens, life in a mobile Ice Age group differed from life in a later farming settlement, where population density, diet, sanitation, and infectious disease followed new patterns. Any number detached from those conditions becomes less an answer than a comforting illusion of precision. This does not mean that the question of prehistoric lifespan is impossible. It means that the answer must remain layered. We can examine broad patterns, identify individuals who reached older ages, and compare the risks faced during different stages of life. What we cannot honestly do is assign one age to every person who lived before history was written. Prehistoric humans were not one population standing still in time. They were many populations moving through changing worlds. Before we ask how long they lived, we must first ask which humans, in which place, during which part of the enormous past. Before a prehistoric child could become an adult, the first years of life had to be survived. This was not a small beginning to a long journey. It was often the most uncertain part of the entire human lifespan. A newborn depended completely on other people for warmth, food, protection, and movement. The child could not follow a migrating group, find water, escape danger, or regulate body temperature as effectively as an adult. Survival began with the body of the mother and quickly expanded to include the attention of relatives and other members of the group. Human infants are unusually dependent compared with the young of many other mammals. Their brains and bodies continue developing for years, and this long period of dependence is one reason childhood became so closely tied to social care. In prehistoric communities, that dependence existed without antibiotics, modern obstetric care, vaccines, or reliable treatment for dehydration and infection. Yet, it would be wrong to imagine every birth as a catastrophe. Human populations continued for thousands of generations because many mothers and children did survive. The important point is that the margin for recovery was narrow. A difficult birth, a premature infant, a period of poor nutrition, or an infection that would now be treatable could become fatal. Childbirth itself was shaped by several interacting factors, including the form of the human pelvis, the size and position of the infant, the health of the mother, and the conditions surrounding delivery. Researchers do not reduce this complexity to one simple evolutionary explanation, but they agree that human birth can place serious demands on both mother and child. After birth, the dangers changed rather than disappeared. A baby depended on breast milk or other available foods, and on continuous protection from cold, heat, contaminated water, injury, and disease. Weaning could open another vulnerable period. As a child moved from milk toward the foods eaten by the group, the body faced new pathogens and the possibility that seasonal shortages would reduce both the amount and quality of nourishment. The risks were not identical everywhere. A child growing near a productive coast did not experience the same food pattern as one living in a dry interior or a cold glacial landscape. Some groups moved often, while others remained near dependable resources for longer periods. Some years may have been comparatively generous. Others may have brought failed plant foods, fewer animals, severe weather, or illness spreading through a small camp. Even the archaeological record does not preserve these young lives evenly. The bones of infants are smaller, more fragile, and more easily lost or damaged than adult remains, while burial customs and soil conditions also affect what survives. This means the danger of childhood cannot be measured perfectly from excavated skeletons alone. Archaeological evidence cannot tell us the fate of every child, and comparisons with recent hunter-gatherers must never be treated as direct photographs of prehistory. Still, demographic studies repeatedly show that mortality before adolescence can be high in populations without modern public health systems. This matters because those early deaths strongly lower life expectancy at birth. They also help explain why a prehistoric population might appear extremely young even when some adults lived for many decades. The fragile years were therefore not simply a sad introduction placed before the real story of adult life. They were one of the main forces shaping the numbers we use to describe prehistoric longevity. Every person who later became an experienced hunter, gatherer, parent, craft worker, healer, or elder had once passed through a stage in which survival depended almost entirely on care. Their later age cannot be understood without remembering those who never reached it. When we ask how long prehistoric humans could really live, the first honest answer is not a number. It is a condition. Before a long life was possible, childhood itself had to be survived. When people hear that prehistoric life expectancy may have been low, the number often feels like a direct measure of adult life. Yet much of that number may have been shaped by children who never reached adulthood. In any population where deaths are concentrated in infancy and early childhood, the average age at death falls quickly. This does not require every adult to die young. It only requires enough very short lives to be included in the calculation. A child who died during the first year contributed almost no years to the average, while an adult who lived into the 40s contributed many. When these very different lifespans are combined, the result can look like a world in which everyone died near the same young age, even though the real pattern was divided between early loss and longer survival. This is why the youngest members of a prehistoric community matter so much to the question of longevity. They were not a small statistical detail. Their mortality could shape the entire picture we form of how long humans lived. The problem becomes more complicated because prehistoric children are not always visible in the archaeological record in the same way as adults. Infant and child bones are smaller, thinner, and more vulnerable to decay, soil chemistry, water movement, animal disturbance, and excavation damage. Some may have been buried differently from adults, placed in locations that have not survived, or treated according to customs that left little archaeological trace. In some sites, children are well represented. In others, they appear fewer than researchers would expect from any living population. That absence cannot automatically be interpreted as evidence that few children died. It may instead reflect preservation, burial practice, discovery, or the limits of the sample. This uncertainty matters because a cemetery or group of skeletons is not a complete census. It is only the portion of a population that entered the archaeological record and remained there long enough to be found. The children missing from the ground may also be missing from later estimates, while the children whose deaths lowered life expectancy in real life may be undercounted in the surviving evidence. Researchers therefore combine skeletal data with demographic models, comparative studies, and careful examination of burial context, but no method can reconstruct every lost life. We must also avoid treating all childhood deaths as if they had the same cause. Some may have followed complications at birth. Others may have resulted from infection, dehydration, injury, poor nutrition, congenital conditions, or periods when a mother's health and food supply were strained. The balance of these risks changed across climates and communities. A mobile group in a cold environment faced different pressures from a settled population living near abundant water. The point is not that prehistoric childhood was uniformly hopeless. Many children survived, learned, played, traveled, and became adults who carried knowledge into the next generation. The point is that early mortality was unevenly concentrated, and that concentration strongly affected every average calculated from birth. Once a child passed through those fragile years, the arithmetic changed. The deaths that had already occurred among infants no longer described that survivor's personal future in the same way. A 10-year-old, a 15-year-old, and a 20-year-old each stood at a different point in the mortality pattern. Their remaining chances were still uncertain, but they were not identical to the chances they had faced as newborns. This distinction brings us closer to the real meaning of prehistoric lifespan. The low average did not belong equally to every person. It was partly built from lives that ended before they could reveal how long the human body might have continued. To understand how long prehistoric humans could truly live, we must remember both groups at once: the children whose early deaths pulled the average downward, and the survivors whose later years were hidden behind that same number. Surviving the first years of childhood did not make a prehistoric person safe, but it changed the balance of risk. A newborn could do almost nothing without constant care. An older child could walk with the group, eat a wider range of foods, communicate discomfort, learn where water and shelter could be found, and gradually take part in ordinary work. The body was also no longer passing through the same extreme vulnerability associated with birth, infancy, and early weaning. In populations without modern medicine, deaths could still occur at every age, yet mortality was often concentrated most heavily near the beginning of life. Once a child moved beyond that dangerous period, the chance of reaching later childhood and adulthood generally improved. This is not the same as saying that childhood suddenly became easy. Growth required energy, and a child needed enough food, not only to remain alive, but also to build bone, muscle, teeth, and a developing brain. Infection could interrupt that growth. A season of scarcity could leave effects that continued after food became more available. Repeated illness, parasites, injury, or poor nutrition could weaken one child more than another, even within the same community. Archaeologists sometimes find interruptions in tooth enamel or signs of physiological stress in growing skeletons, but such evidence must be interpreted carefully. It can show that the body passed through difficulty, yet it does not always reveal the precise cause or duration. The skeletons that survive also create a form of selection. A child who endured stress and survived into adulthood may carry traces of the same event into an older skeleton. The evidence therefore contains both vulnerability and recovery, although neither is preserved completely. For the central question of prehistoric longevity, This change after childhood is essential. A life expectancy calculated from birth combines the risks of a helpless infant with the different risks faced by a mobile and increasingly capable young person. It cannot tell us how long the second person might live after the first stage had already been survived. Social development also altered survival. Older children could watch adults prepare food, maintain fire, identify plants, shape tools, recognize animal signs, and respond to weather. They did not need to master these abilities all at once. Human childhood is unusually long, allowing learning to continue while children receive food and protection from others. This extended dependence was costly for a group, but it also gave young humans time to acquire complex local knowledge. A child who knew which path led back to camp, which water could be approached safely, or how to stay close during movement had advantages that an infant could not possess. Brothers, sisters, grandparents, and other companions may also have shared supervision and food, although the form of such help differed between communities. We should not turn this cooperation into an idealized picture. Care could fail, resources could be insufficient, and groups could experience conflict or loss. Survival remained conditional on the health of caregivers and the wider fortunes of the group. As later childhood approached, new dangers appeared. Greater independence meant more movement, more contact with tools, fire, water, steep ground, animals, and unfamiliar places. A stronger body could resist some threats while entering the range of others. The young person was becoming less vulnerable to the conditions that threatened an infant, but increasingly exposed to the work and travel of the community. This gradual exchange of risks helps explain why there was no single moment when survival became secure. It also shows why prehistoric lifespan must be studied stage by stage. Those who reached adolescence had already survived repeated biological and environmental tests. Their presence did not erase the children who died earlier, but it meant that the low average at birth no longer described their future in the same way. The question was beginning to change from whether life could continue at all to how long an increasingly capable human body could endure the hazards of adulthood. Adolescence changed the conditions of survival once again. A young prehistoric person was no longer as dependent as a child, but was not yet carrying the full experience of an older adult. The body was growing stronger, movement became easier, and the range of useful skills expanded. At the same time, greater ability brought greater exposure. A person who could travel farther could also fall farther from help. Someone learning to handle stone edges, wooden shafts, fire, water, or heavy loads gained valuable knowledge, but also entered situations in which a small mistake could cause a serious wound. There was no universal prehistoric age at which childhood ended. Growth rates differed among human species, and customs must have differed between communities. The archaeological record can preserve injuries and physical stress, but it rarely reveals the exact task or moment that produced them. Even among Homo sapiens, maturity was not a single event shared in exactly the same way across thousands of generations. The transition was probably gradual: more distance from caregivers, more responsibility, more observation of adult work, and repeated practice within the landscape. Studies of recent hunter-gatherer societies show that adolescents often contribute increasingly to food production and social life, but such societies are comparisons rather than direct copies of the Paleolithic past. They remind us that learning to live independently can take years, especially when survival depends on detailed knowledge that cannot be gained from instinct alone. A young person had to recognize paths, weather, animal behavior, edible foods, dangerous plants, water sources, and the habits of other people. Strength without that knowledge could not guarantee survival. The risks of adolescence were therefore partly physical and partly connected to inexperience. A growing body demanded energy. Periods of poor nutrition could slow development or reduce the strength available for work and recovery. Infection could become dangerous after an injury, while repeated illness could leave a young person less able to keep pace with a mobile group. Yet, adolescence should not be imagined as a continuous test of bravery. Much of life probably consisted of ordinary learning, repeated tasks, rest, conversation, and gradual participation. Young people may have gathered nearby foods before traveling farther, carried lighter loads before heavier ones, or watched tools being made before using them independently. The safest knowledge was often built slowly. Other people remained important during this transition. Adults could demonstrate techniques, share food, warn of dangerous places, or reduce the consequences of a failed attempt. Companions of similar age could also learn together. None of this removed the possibility of loss, and the amount of protection available must have varied with group size, resources, health, and circumstance. A small community facing hunger or movement could not always shelter every member from risk. Still, adolescence did not necessarily mean being abandoned to survive alone. Human development remained social, even as independence increased. For the question of prehistoric lifespan, this stage matters because it stood between two different mortality worlds. Those who reached adolescence had already survived the high dangers of infancy and early childhood. They were closer to adult strength, yet they had not accumulated the experience that might help an older person avoid certain hazards. Some would die before becoming fully established adults. Others would pass through this period and enter years in which the causes of death were distributed differently. The transition helps explain why life expectancy could not be treated as one unchanging chance assigned at birth. Each stage altered both the body and the surrounding risks. A prehistoric adolescent was not protected by modern medicine, formal safety systems, or reliable rescue. But neither was that young person simply helpless. Survival rested on a developing combination of strength, knowledge, judgment, and support. Reaching adulthood required more than the passing of time. It required learning how to move through a particular world without allowing one unfamiliar danger to bring a promising life to an early end. A prehistoric adult did not need to face a dramatic disaster for life to end early. Many dangers were ordinary, familiar, and difficult to avoid completely. A cut from a stone edge, a fall on uneven ground, a burn near a fire, or a twisted joint during travel could become serious when there was no surgery, no antibiotics, and no reliable way to prevent infection. The injury itself was only part of the danger. A wound that seemed small on the first day could swell, become painful, and weaken the body over time. If fever followed, survival depended on the person's strength, the location of the injury, the cleanliness of the wound, and the care available from others. Some people recovered, as healed fractures and other signs of survival show. Others may have died from injuries that would now be considered treatable. Infection did not always begin with visible trauma. Respiratory illness, intestinal disease, parasites, and infections connected with teeth or gums could also become dangerous. A damaged tooth could make eating difficult and create a path for infection. Diarrhea could lead to severe dehydration, especially when food was scarce or water quality was poor. Illness did not affect every group in the same way. Mobile communities, small camps, climate, contact with animals, population density, and access to clean water all changed which diseases were likely to spread. It would be misleading to imagine one universal prehistoric disease environment. Even so, the absence of modern treatment meant that the body often had to recover with rest, nourishment, and social support alone. Food shortage created another kind of risk. Prehistoric people were not always starving, and many groups possessed deep knowledge of plants, animals, seasons, and landscapes. Yet even good knowledge could not prevent every failed hunt, drought, harsh winter, flood, or sudden change in animal movement. A short period of scarcity might weaken the body without causing immediate death. Repeated shortages could reduce resistance to infection, slow healing, and make ordinary work harder. The danger often came through accumulation. A person already weakened by illness could struggle to travel. Someone unable to travel might lose access to food. A small problem could become a chain of larger ones. Accidents were also part of daily movement. Rivers, steep slopes, ice, loose stone, falling branches, fire, and large animals all carried risks. Hunting could be dangerous, but so could gathering food, carrying a child, crossing water, or moving camp. Archaeological evidence preserves some fractures and injuries, yet it cannot reveal every fatal accident. A person who drowned, disappeared, or died where remains were not preserved may leave no trace at all. Violence between individuals or groups was another possible cause of death, and some prehistoric skeletons show injuries consistent with conflict, but the evidence varies greatly by place and period. It would be inaccurate to describe all prehistoric life as constant warfare. Violence existed, but so did long stretches of ordinary cooperation, exchange, childcare, food preparation, and rest. Childbirth remained a particular danger for women, while pregnancy and nursing increased nutritional demands and could leave the body more vulnerable during periods of shortage or illness. Men and women also may have faced different patterns of injury depending on their work and movement, although these patterns were never identical across all communities. The important point is that adult mortality did not come from one dominant enemy. It emerged from many risks that could overlap: injury, infection, hunger, exposure, childbirth, accidents, and sometimes violence. Reaching adulthood improved a person's chances compared with infancy, but it did not create a protected middle of life. Survival still depended on the body, the environment, experience, and the willingness or ability of others to help. These ordinary causes of early death explain why some adults never reached old age, even though the human body itself was capable of continuing for many more years. Adult life did not carry one equal level of danger for every prehistoric person. Two people of the same age, living in the same group, could face different chances of surviving the next year because their bodies, responsibilities, past injuries, and access to help were not the same. Biological sex could influence some risks, but not in one simple direction. Pregnancy and childbirth placed demands on the body that men did not experience. Blood loss, obstructed labor, infection, poor nutrition, and complications after birth could threaten both mother and infant, especially without modern surgical care or antibiotics. Yet the exact scale of maternal mortality in deep prehistory cannot be calculated from skeletons alone. Direct archaeological evidence of death during childbirth is rare, and the absence of a fetus within a woman's pelvis does not prove that birth was safe. Many deaths left no preserved relationship between the mother and child. Men may have faced higher exposure to certain forms of trauma in some communities if they traveled farther, hunted large animals, participated more often in conflict, or performed particular kinds of heavy work. But these roles cannot be assumed for every place and period. Skeletal studies sometimes reveal differences between males and females in healed fractures, weapon injuries, joint wear, or dental disease, yet patterns vary widely. A result from one Neolithic cemetery cannot be transferred automatically to mobile hunter-gatherers living thousands of years earlier. Even estimating biological sex from incomplete remains carries uncertainty, so the most honest conclusion is that adult risks were often unequal without being universally divided into one male pattern and one female pattern. Individual health created another layer. A person carrying an old fracture, chronic joint damage, severe tooth loss, or the effects of childhood stress might have less strength available during migration, cold weather, or food shortage. Another person of the same age might remain physically capable for much longer. This matters directly to the question of prehistoric lifespan. The age a human body could potentially reach was not the age every body had an equal chance of reaching. Longevity emerged from repeated encounters between physical condition and circumstance. A strong adult could still die in a single accident, while someone with serious impairment could survive for years if the group provided food, protection, and time to recover. Environment also distributed danger unevenly. A coastal community might have dependable food, but face storms, drowning, and injuries on rocks. A group in a cold interior might depend more heavily on seasonal animal movements and protection from exposure. Tropical environments could offer food across more of the year, while also supporting different parasites and infectious diseases. Dry landscapes made knowledge of distant water sources especially important. None of these settings was simply safe or dangerous. Each created its own pattern of risk, and that pattern could change from one season to the next. Social position and relationships may have mattered as much as physical strength, although they are difficult to see in bone. A person surrounded by relatives and trusted companions may have received food during illness or assistance after injury. Someone isolated by conflict, loss, or group movement may have had fewer chances to recover. Archaeology can sometimes identify survival after severe injury, but it cannot tell us every reason help was given or withheld. Age itself added another difference. An experienced adult might avoid hazards that a younger person overlooked, while accumulated wear, reduced mobility, or repeated pregnancies could gradually narrow the margin for recovery. Adult mortality was therefore not a single road that everyone followed at the same speed. It was a collection of unequal paths shaped by reproduction, work, illness, injury, environment, experience, and care. Some adults were removed early by dangers others never faced. Some survived conditions that appear severe, even by modern standards. Before asking how many years prehistoric humans could live, we must recognize that the opportunity to reach those years was never distributed evenly. The human body did not begin failing at 30, simply because many prehistoric populations had low average life expectancies. Once a person survived infancy, childhood, and the uncertain passage into adulthood, the body could continue functioning for many more years. Bones could heal, muscles could remain useful, and knowledge could deepen even as physical strength gradually changed. Humans are a long-lived primate, and the possibility of extended adult life is not a recent invention created by hospitals or modern comfort. Medicine has allowed far more people to approach old age, but it did not create the underlying human capacity to live for decades. That capacity had to exist before cities, writing, or organized healthcare, even though prehistoric conditions often prevented it from being fully expressed. This distinction between capacity and outcome is central to the question of how long prehistoric humans could really live. A person may possess a body capable of reaching 50, 60, or beyond, yet die much earlier from infection, injury, childbirth, hunger, or exposure. The early death does not reveal the body's maximum potential. It reveals the danger of the circumstances surrounding it. In the same way, the presence of an older adult does not prove that everyone had a good chance of reaching that age. It shows that the combined barriers of childhood mortality, accident, disease, and environmental stress were sometimes crossed. Evidence from living hunter-gatherer populations helps illustrate this pattern. Although these communities are not direct replicas of prehistory, their average life expectancy at birth can be low because many deaths occur early, while individuals who survive childhood may continue into their 50s, 60s, or occasionally later. Researchers have also noted that humans live longer than other great apes, including under conditions without modern medicine. This suggests that a relatively long adult lifespan is part of human life history rather than a completely modern development. The reason is not likely to be one feature alone. Comparative research on human and chimpanzee mortality indicates that the difference is visible not only in exceptional maximum ages, but across patterns of adult survival. Humans, therefore, appear adapted to a slower life history in which development, skill acquisition, reproduction, and support between generations can extend across many years. Human development is slow, childhood learning is prolonged, and adults can continue producing food, sharing knowledge, and assisting relatives long after they first reproduce. A long life may therefore have carried value beyond simply having more children. Older individuals could retain knowledge of seasonal changes, difficult routes, food processing, tool-making, social relationships, and past periods of scarcity. Yet the existence of those possible benefits does not mean natural selection designed a precise age at which every human should die. Aging is gradual and uneven. Teeth wear, joints change, vision weakens, injuries accumulate, and recovery may become slower. One person might remain active despite visible degeneration, while another could become limited much earlier. Prehistoric bodies were also shaped by demanding movement and work, but physical activity alone should not be imagined as either a guarantee of health or a cause of rapid destruction. Its effects depended on nutrition, illness, workload, injury, and rest. The important point is quieter. The body that entered adulthood was not standing at the edge of an automatic collapse. It contained the biological possibility of decades still to come. Whether those decades were reached depended on repeated survival through ordinary hazards. Every additional year required the body to repair damage, resist infection, find enough energy, and remain connected to people who could sometimes compensate for temporary weakness. This is why low prehistoric life expectancy should not be confused with a short biological lifespan. One describes what happened across a population exposed to severe mortality. The other describes how long a human organism might continue when enough dangers were avoided. The distance between those two measures was where many prehistoric lives were lost and where a smaller number quietly continued. Humans do not age outside the biological rules that govern other primates, yet the timing of human life is unusual. Compared with chimpanzees and other great apes, humans generally mature more slowly, spend longer learning before becoming fully independent, and can remain alive for a much longer period after reaching adulthood. This difference does not mean that prehistoric people escaped aging or that evolution gave them a protected number of years. Their teeth wore down, joints changed, injuries accumulated, and the body gradually became less able to recover from illness. What differed was the length of the life course within which these changes could unfold. A human adult was part of a species capable of continuing through several decades of work, reproduction, learning, and social participation. The important difference was therefore not freedom from decline, but more time in which adulthood could continue before decline became overwhelming. One way researchers study this difference is by comparing age-specific mortality rather than only the oldest age ever recorded. Maximum lifespan can be distorted by rare individuals, small samples, captivity, or unusually favorable conditions. Mortality across adulthood gives a broader picture. Studies comparing humans with chimpanzees indicate that humans differ, importantly, through lower adult mortality and a longer expected period of life after maturity. Even human populations without modern medicine have included substantial numbers of adults living beyond the ages commonly reached by wild chimpanzees. This pattern suggests that extended adult survival was not created recently, although modern sanitation, food security, vaccination, and medical treatment have allowed many more people to benefit from it. Why this longer human life evolved is still debated. No single explanation has been proven to account for every feature. One group of hypotheses emphasizes the difficulty of obtaining human food. Many resources require years of learning, planning, tool use, cooperation, and knowledge of seasonal landscapes. A long childhood allows these skills to develop, while a long adult life provides more time for the knowledge to repay the energetic cost of learning it. Adults who remained alive could continue producing food and helping younger people long after they had first reached reproductive age. Other hypotheses emphasize food sharing, care of children, and assistance from older relatives, including the possible contribution of post-reproductive women. These ideas are important, but they should not be presented as a simple story in which grandparents alone caused human longevity. Human life history was probably shaped by several interacting pressures, and the balance may have changed across species, environments, and periods of prehistory. The evolutionary meaning of a long life is also different from a promise that any individual will reach old age. Natural selection acts through patterns of survival and reproduction across populations, not by assigning a personal expiration date. Traits that support maintenance and repair can make extended life possible, while external dangers still prevent many bodies from reaching that potential. This helps explain the central prehistoric paradox. The species could possess a relatively long adult lifespan, even while average life expectancy at birth remained low. A child lost to infection, an adult killed by a fall, and an older person surviving into a sixth decade all belonged to the same human biology. Their different ages at death reflected both that biology and the unequal circumstances through which it moved. We must also be careful when extending conclusions backward through the human family. Neanderthals, early Homo sapiens, Homo erectus, and earlier hominins did not necessarily develop or age in identical ways. Fossils can reveal growth patterns, tooth development, skeletal wear, and occasional older individuals, but they cannot provide complete life tables. The clearest statement is therefore a limited one. By the time of our species, and probably through earlier stages of human evolution, adult life had become longer and slower than in our closest living ape relatives. How often prehistoric conditions allowed that distinctive human lifespan to reach its later decades remains a separate question. The human life course does not end when reproduction begins to decline. In our species, adults can remain socially and economically important long after the years in which they first became parents, and women may live for decades after menopause. Men do not experience the same sharp reproductive transition, but aging still changes fertility, strength, health, and the roles they can perform. This pattern of extended later life is unusual enough to have become a major question in the study of human evolution. If natural selection often favors traits that improve the production and survival of offspring, why would the human body maintain itself beyond the period when a woman could bear more children? One proposed answer is that older adults could continue helping relatives who carried some of the same inherited traits. An older woman might provide food, help care for children, share practical knowledge, or reduce the burden carried by her daughters and other relatives. This idea is commonly associated with the grandmother hypothesis. It suggests that survival after reproduction could still influence the success of later generations. Yet it remains a hypothesis, not a complete explanation established for every prehistoric population. Models and observations from some recent societies support parts of it, while other studies question whether grandmothering alone is strong enough to explain the evolution of human longevity. Older men and women may also have contributed in ways that were not limited to direct childcare. A person who had lived through many seasonal cycles could remember where water remained during drought, when particular plants appeared, how animal movements changed, or which routes became dangerous after storms. Skill in making tools, processing food, maintaining social ties, or recognizing signs of illness could improve slowly across adulthood. Physical strength might decline, while judgment continued to deepen. In a small community, knowledge held by one experienced person could matter during an unusual season, especially when younger adults had never encountered the same conditions. Archaeology cannot usually tell us exactly who taught whom, and it cannot prove that every older person held a respected position. Some may have been limited by pain, tooth loss, poor vision, or reduced mobility. Others may have remained active for years. Social value was therefore not guaranteed by age, just as physical weakness was not guaranteed at a particular birthday. The wider point is that human survival may have been connected to contributions extending beyond direct reproduction. Long childhoods required food, protection, and teaching from several people. Adults raising dependent children could benefit from assistance, whether it came from grandparents, siblings, unrelated companions, or other members of the group. This broader pattern of cooperative care may have made an older survivor useful, even when that person no longer performed the most physically demanding tasks. It may also have strengthened the group's ability to absorb temporary loss, because knowledge and care were not concentrated in only one pair of parents. At the same time, usefulness should not be treated as the reason every individual was allowed to live. Prehistoric people were not calculating evolutionary value. They lived within relationships shaped by attachment, obligation, memory, conflict, and circumstance. Evolutionary explanations describe patterns across many generations. They do not reveal the private motives of one family around one fire. For the question of lifespan, life beyond reproduction, offers an important clue rather than a final answer. It shows that later adulthood was not necessarily an empty biological remainder. The human body could continue supporting memory, care, production, and social connection after the peak years of fertility. That possibility may have helped make longer lives advantageous, but it could only matter when individuals survived the earlier dangers of childhood, injury, infection, and scarcity. An older adult in prehistory was therefore both biologically possible and demographically uncommon in many settings. Each such person represented not an exception to human nature, but one expression of a life course that had room for more than reproduction alone. A skeleton does not preserve the date of a person's birth, but it does preserve a sequence of changes that occurred while the body was growing, working, repairing itself, and aging. Researchers estimate age at death by comparing those changes with patterns observed in people whose ages are known. The process is not like reading a number carved into bone. It is closer to assembling several imperfect clocks, each of which runs at a slightly different speed. Teeth provide some of the clearest clues during childhood because they form and erupt in a broadly ordered sequence. The appearance of milk teeth, the development of permanent crowns and roots, and the timing of eruption can place a young individual within a relatively narrow age range. Bones also record growth. Long bones lengthen from areas called growth plates, and different parts of the skeleton gradually fuse as maturity approaches. Because development follows a more predictable sequence than later degeneration, the age of a child or adolescent can often be estimated more closely than the age of an adult. Once growth is complete, the task changes. Researchers can no longer ask which tooth is forming or which growth plate has fused. They must examine slower and more variable signs of use and aging. One important area is the pubic symphysis, the surface at the front of the pelvis where the two sides meet. Its shape and texture tend to change across adulthood. Another is the auricular surface, where the pelvis joins the sacrum at the back. The ends of certain ribs also alter in form over time. These regions can be compared with documented reference samples, producing an estimated range rather than an exact birthday. Teeth continue to offer evidence in adulthood, but they must be treated cautiously. Wear may increase with age, yet it is also affected by diet, food preparation, grit, tool use, and individual habits. A person eating coarse foods may develop heavily worn teeth earlier than someone of the same age whose food was softer. Tooth loss and dental disease can reveal long use and poor oral health, but they do not translate directly into a fixed number of years. The same uncertainty applies to arthritis, joint damage, and bony growths. These changes may become more frequent with age, but workload, injury, genetics, nutrition, and disease can accelerate or delay them. A heavily worn skeleton is therefore not automatically an extremely old skeleton. It may belong to a younger person whose body endured unusual strain. This difference between chronological age and biological condition is one of the central limits of skeletal analysis. Two people who died at the same age may leave bodies that appear very different, while two skeletons that look similar may belong to people separated by many years. Researchers gain greater confidence when several indicators point in the same direction. The pelvis, ribs, teeth, joint surfaces, microscopic bone structure, and overall pattern of degeneration can be considered together. Even then, the conclusion may be broad, perhaps a young adult, a middle-aged adult, or someone older than 50. The further adulthood advances, the more individual variation tends to obscure the clock. This is especially important in prehistoric research, where skeletons may be incomplete, damaged, or drawn from populations unlike those used to create modern reference standards. An age estimate is therefore a scientific judgment expressed with uncertainty, not a hidden fact recovered without error. This does not make skeletal evidence useless, it makes careful interpretation necessary. Teeth and bones can reveal that children, mature adults, and older individuals were present. They can show that some people lived long enough to accumulate degeneration, lose teeth, or recover from injuries. What they usually cannot provide is a perfect list of exact ages. When we ask how long prehistoric humans lived, The surviving body answers slowly through ranges, comparisons, and traces of time rather than a precise final number. Children are often easier to age from their remains because growing bodies follow a sequence. Teeth form, emerge, and replace one another in an order that is more regular than the changes produced by adult aging. Long bones lengthen from growth plates, parts of the pelvis and skull continue to develop, and separate pieces of bone gradually fuse. These processes do not occur at exactly the same age in every child, but they tend to follow a recognizable pattern. When several of these signs are present together, researchers can often estimate age within a narrower range than they can for a mature adult. A young child may be placed within a span of months or a few years, while an older adult may only be classified broadly. Teeth are especially useful because their development begins before birth and continues through childhood and adolescence. The crowns and roots of different teeth form in stages, and these stages can be observed even when a tooth has not yet erupted. This means that a child's dental age does not depend only on which teeth were visible in the mouth. Researchers can examine the teeth still developing inside the jaw and compare them with well-documented developmental sequences. Permanent teeth usually provide another set of clues as they replace the first teeth, and the completion of root formation can help estimate age in later childhood. Dental development is not perfectly identical across all populations, and illness or severe malnutrition can influence growth, but tooth formation is generally less affected by daily activity than adult tooth wear. The skeleton provides a second clock. At birth, many bones are not fully fused. As the child grows, the shafts and ends of long bones change in size and eventually join. Different bones fuse at different stages, producing a sequence that can be compared with reference material. Before fusion is complete, the length of certain bones may also help estimate age, particularly in infants and young children. Yet this method requires caution because growth can be slowed by poor nutrition, chronic disease, or other forms of stress. A small body is not always a young body. Size alone can mislead, so researchers prefer to combine it with dental development and the state of growth plates. The relative predictability of development is the main reason children are easier to age. Adult aging does not move through such a clear sequence. After the skeleton has matured, later changes are shaped by work, injury, disease, diet, genetics, and the environment. One 40-year-old may show extensive joint wear, while another shows little. By contrast, a child whose first permanent molars are forming and whose long bone ends remain unfused occupy a more limited stage of development. Even so, the prehistoric child remains present serious difficulties. Their bones are thin, fragile, and easily damaged. Small bones may be missed during excavation, destroyed by soil conditions, or scattered before burial is discovered. Some skeletons are incomplete, leaving only a few indicators from which to estimate age. Burial customs may also cause certain ages to be underrepresented at a site. A precise method cannot recover information that was never preserved. For the study of prehistoric lifespan, the better aging of children creates an important contrast. Early deaths may be easier to place within the life course, while the ages of older adults remain blurred. This imbalance can make the beginning of the mortality pattern look sharper than its later end. We may know that a child died at roughly 3 or 6 years, yet describe an older person only as over 40 or over 50. The record, therefore, reveals childhood with greater chronological detail, while allowing later survival to fade into broad categories. Understanding this difference helps prevent another mistake, assuming that the lack of exact ages among older skeletons means that older people were absent. Sometimes the uncertainty belongs not to their lives, but to the limits of the biological clocks that remain. Age becomes harder to read from a skeleton after the body has completed its growth and moved into later adulthood. In childhood, teeth and bones pass through ordered stages. In older adults, researchers must rely mainly on degeneration, remodeling, and accumulated wear, and these processes do not advance at the same speed in everyone. A person who died at 52 may show more joint damage than someone who lived into the 60s. Workload, injury, nutrition, disease, genetics, and ordinary variation can all make the skeleton appear biologically older or younger than its chronological age. For this reason, the phrase over 50 should not be understood as a precise boundary in the body. It is often a practical category created because many skeletal methods lose the power to separate later decades reliably. Surfaces of the pelvis may continue changing with age, the ends of the ribs may become more irregular, joints may develop osteoarthritis, teeth may wear or be lost, and the internal structure of bone may be remodeled. Yet these signs do not form a clean ladder from 50 to 60, then 60 to 70. Some reach advanced-looking stages early, others change slowly. Many traditional methods also have a final stage into which people of several different ages can fall. Once a skeleton reaches that stage, the method may recognize that the person was older without revealing how much older. This produces wide estimates and categories such as 50 years or more. Such a category may contain people separated by 20 or even 30 years of life. Another difficulty comes from the reference collections used to build aging methods. Researchers compare an unknown skeleton with remains from people whose ages at death were documented. If the reference sample contains relatively few older individuals, or comes from a population with different health, ancestry, diet, and patterns of physical work, its stages may not fit a prehistoric population perfectly. Statistical methods can also pull an estimate toward the ages most common in the reference sample, a problem sometimes called age mimicry. This can make very old adults appear younger in reconstructed demographic profiles and can crowd many individuals into broad middle adult groups. The archaeological record adds further uncertainty. Older skeletons may be incomplete, fragile, distorted by soil pressure, or missing the pelvis, ribs, or teeth needed for several methods. A skull alone may offer fewer dependable indicators than a well-preserved complete skeleton. Combining multiple parts of the body usually gives a stronger estimate, but agreement between indicators does not turn an estimate into certainty. New approaches using microscopic bone structure, chemical changes, imaging, and computational models may improve accuracy in some cases. They still require validation, appropriate samples, and enough preserved material, and they do not remove all biological variation. This uncertainty has a direct effect on the question of prehistoric longevity. When older adults are underestimated or compressed into younger categories, an ancient population can appear to contain fewer elders than it truly did. That distortion then affects estimates of adult survival, family structure, accumulated knowledge, and the social presence of later life. If many older people are recorded only as 50+, we cannot simply count exact numbers of people who reached 60 or 70. A person placed in that open category may have died at 51, 64, or perhaps later. The evidence can show that later adulthood existed, sometimes with extensive tooth loss, healed injury, and degenerative change. It usually cannot divide those survivors into exact birthdays. The blurred upper end of the record therefore encourages humility. The absence of a skeleton confidently labeled 70 does not prove that no one reached 70. At the same time, a broad estimate cannot be stretched into proof that someone did. The most truthful reconstruction must preserve the range. After 50, the bones continue to carry time, but their clock becomes quieter, less regular, and harder to translate into years. A healed bone preserves something that an injury at the moment of death cannot: the passage of time afterward. When a fracture occurs, the body begins a sequence of inflammation, repair, and remodeling. New bone forms around the damaged area, gradually stabilizing it and changing its shape. If archaeologists find this repair in an ancient skeleton, they know that the person did not die immediately from the injury. The individual lived long enough for healing to begin, and sometimes long enough for the repaired bone to be reshaped through months or years of continued use. This evidence does not reveal every detail of the person's recovery, but it places survival directly into the body. Prehistoric skeletons contain fractures that healed neatly, others that joined at unusual angles, and joints altered by compensating for an old injury. A poorly aligned leg might have shortened a stride. Damage to an arm could have changed the way tools were held or loads were carried. The body could adapt by shifting weight and relying more heavily on other muscles and joints. These adjustments might allow a person to remain active, although they could also produce pain and additional wear. The presence of healing, therefore, tells us more than the fact that someone remained alive. It can show that life continued under changed physical conditions. Yet care is required when interpreting what made that survival possible. A healed fracture is not automatic proof that an injured person was helpless or received constant nursing. Some injuries permit limited movement, and human bodies can recover without specialized treatment. A person might have rested, protected the injured part, or continued working with difficulty. On the other hand, severe injuries can make walking, gathering food, or defending oneself temporarily impossible. In those cases, survival may have depended on food sharing, protection, transportation, or the willingness of others to wait. The skeleton can reveal the biological need created by an injury, but it rarely preserves the exact social response. Archaeologists must distinguish what the bone proves from what the surrounding evidence only suggests. This caution is important because healed injuries are often used to create comforting stories about universal prehistoric compassion. Cooperation and care clearly formed part of human life, but every wound cannot be turned into a complete account of kindness. The same evidence also should not be reduced to a story of individual toughness. Recovery requires energy, time, and freedom from new dangers. Even when no formal treatment existed, clean water, warmth, food, rest, and protection could change the outcome. The ability to receive those things was connected to the resources and relationships around the injured person. Healed trauma also helps explain why skeletal populations contain only survivors of certain events. A fatal fracture may leave damage without repair, while an injury to soft tissue may leave no mark on bone at all. Those who recovered are visible because their bodies had time to record the recovery. Those who died from infection, blood loss, organ damage, or an accident that did not affect bone may remain silent. The archaeological record can therefore show that survival after injury occurred, but it cannot tell us how often comparable injuries ended in death. For the question of prehistoric longevity, healed bones offer a limited but powerful answer. They show that some people crossed barriers that might easily have shortened life. A fracture, disability, or serious wound did not always mark the end. The body could repair itself, behavior could change, and other people may sometimes have helped create the time necessary for healing. Each repaired injury represents additional days, seasons, or years that an average lifespan cannot describe. It does not prove that the person became old, and it cannot reveal every unseen hand involved in recovery, but it proves that a threatened life continued beyond the moment when it might have ended. Among the prehistoric individuals whose bodies still carry evidence of long survival, Shanidar I has become one of the most widely discussed. His partial skeleton was discovered in Shanidar Cave in the Zagros Mountains of present-day Iraqi Kurdistan. He was a Neanderthal man who lived tens of thousands of years ago and is generally estimated to have died between about 35 and 45 years of age. That number may not sound old beside a modern lifespan, but it represented a substantial adult life within the surviving Neanderthal record. More importantly, the years he reached were lived with several physical conditions that could have made ordinary movement, communication, and food gathering more difficult. His skull shows an old injury around the left eye socket. The damage probably reduced or destroyed vision in that eye, although the exact effect cannot be recovered with complete certainty. His right arm was severely underdeveloped and damaged. Parts of the lower arm and hand were absent from the recovered remains, and researchers have debated whether they were lost through injury, disease, or deliberate removal. The shoulder and upper arm also show long-term abnormalities. His right foot contained a healed fracture, and changes in his legs and joints suggest that he probably walked with a limp. These were not all fresh injuries received shortly before death. The bones had remodeled, showing that he continued living after at least some of the damage occurred. Later examination of his ear canals identified large bony growths that would probably have caused significant conductive hearing loss. Hearing difficulty would have carried particular consequences in a mobile hunting and gathering world. Voices, falling stones, nearby animals, and warnings from companions could be important signals. Combined with impaired vision, limited use of one arm, and difficulty walking, reduced hearing may have narrowed the ways Shanidar 1 could respond quickly to danger. Yet the skeleton does not show a body that simply stopped participating in life. It shows adaptation continuing over time. He moved enough for his joints and bones to record the effects of compensation. He ate long enough for his teeth to become heavily worn. He survived through repeated seasons in a rugged landscape. This is why Shanidar 1 is often presented as evidence that other Neanderthals supported an impaired group member. The interpretation is reasonable, especially because several of his conditions may have reduced his ability to obtain all necessary food independently or to keep pace during difficult movement. Companions may have shared food, adjusted their travel, offered protection, or allowed him to contribute through tasks that required less mobility. However, the skeleton does not preserve a daily record of that assistance. It cannot tell us who helped him, how often help was needed, or what he could still accomplish alone. Disability does not always mean total dependence. A person may develop new techniques, use the stronger side of the body, choose less demanding work, and rely on detailed knowledge rather than speed. Shanidar 1 may have received substantial care, while also remaining a capable participant in his group. These possibilities do not contradict one another. His importance lies less in proving a single story of compassion than in showing that Neanderthal survival could be flexible. Physical limitation did not automatically remove a person from the community or bring life to an immediate end. For the question of prehistoric longevity, Shanidar 1 is not evidence that most Neanderthals reached 40, nor that 40 was their maximum possible age. One individual cannot define the mortality pattern of an entire species. His estimated age is also a range rather than a precise number. What he demonstrates is narrower and more secure. A Neanderthal could survive into later adulthood after injuries and impairments that had altered much of his body. His life continued not because prehistoric danger was absent, but because bodies, behavior, and perhaps social relationships sometimes created room beyond it. The Neanderthal known as La Chapelle aux Saints 1 was discovered in 1908 in a small cave in southwestern France. His skeleton, preserved more completely than most Neanderthal remains known at the time, quickly became one of the most influential fossils in the study of human origins. He was called the Old Man of La Chapelle because his bones showed extensive changes associated with later adult life. Modern estimates cannot provide an exact age at death. One analysis of the pelvic surface suggested an age near 60 with a wide margin of uncertainty, while other descriptions simply classify him as an older adult. The uncertainty matters. His skeleton demonstrates survival into a relatively advanced stage of Neanderthal life, but it cannot reveal a precise birthday. His body carried substantial evidence of degeneration. Changes affected parts of his spine, shoulders, hands, and hips. Several vertebrae showed osteoarthritis, while the left hip was especially damaged. Movement may have been painful, and some ordinary activities probably became slower or more difficult. Yet these conditions did not necessarily force him into the permanently bent posture once used to represent all Neanderthals. The first reconstruction of his skeleton presented Neanderthals as stooped, primitive figures, partly because the researcher interpreted the individual's diseased joints as normal features of the species. Later examinations showed that Neanderthals were fully upright, and that some elements of the old reconstruction reflected assumption rather than anatomy. Even the effects of La Chapelle's joint disease on his own posture remain more complicated than the familiar image suggests. His mouth has also played an important part in the story. He had lost several teeth before death, and bone had healed along parts of the empty gums, showing that he survived after the teeth were gone. Earlier accounts sometimes portrayed him as almost entirely toothless and unable to chew without others preparing every meal for him. A closer study of the jaw and surviving teeth produced a more cautious picture. Some front teeth were probably still present and functional, while much of the tooth loss affected the teeth farther back in the mouth. Disease or infection may have caused additional loss close to the time of death. He may have benefited from softer or processed foods, but the skeleton cannot tell us exactly what he ate or whether someone ground every meal for him. This distinction does not remove the possibility of care. Severe hip and spinal disease, reduced chewing ability, and the ordinary limitations of aging could have made support valuable. Food sharing was already part of Neanderthal social life, and an older adult did not necessarily need to obtain every portion alone. Other people may have brought food, processed difficult items, or allowed him to perform tasks suited to his remaining abilities. At the same time, age and disease should not be confused with complete helplessness. He may still have walked, worked, communicated, and contributed knowledge despite discomfort. The most reliable conclusion is that his life continued while several parts of his body were changing and deteriorating. Recent research has even proposed that some unusual damage in his spine and hip could reflect a chronic infection such as brucellosis, in addition to ordinary osteoarthritis. That diagnosis remains a scientific interpretation rather than a certainty, but it reminds us that an ancient skeleton can contain overlapping conditions rather than one simple disease. La Chapelle aux Saints, one cannot tell us how often Neanderthals reached his stage of life. A single survivor cannot define the lifespan of an entire population. He does show, however, that a Neanderthal body could endure long enough to lose teeth, develop extensive joint disease, and continue living after those changes had begun. His importance lies not in proving that old age was common, but in preventing us from imagining that it was impossible. Food in prehistory was never simply abundant or scarce. The same landscape could provide more than a group could immediately eat during one season, and very little during another. Ripe fruits, nuts, roots, shellfish, fish runs, migrating herds, eggs, honey, and edible leaves did not appear in equal amounts throughout the year. Their availability depended on rainfall, temperature, animal movement, plant growth, and local geography. People who lived by hunting, gathering, fishing, or combining these activities needed to understand when each resource appeared and how long it would remain available. This knowledge could make a difficult environment productive, but it could not remove uncertainty from it. A storm could interrupt fishing, a dry season could reduce water and plant foods. Herds could change direction, a cold interval could shorten the growing season. The question of prehistoric lifespan is therefore connected not only to how much food existed, but to whether enough of the right food reached a person repeatedly across many years. A community could eat well for much of the year and still pass through a dangerous seasonal gap. Short shortages did not always cause immediate death. The body can use stored energy for a time, reduce activity, and recover when food returns. The deeper danger came when scarcity lasted too long, returned too frequently, or arrived while someone was already ill, injured, pregnant, nursing, very young, or old. Insufficient energy could slow healing and weaken the ability to resist infection. A person who normally survived ordinary physical demands might become vulnerable when several pressures overlapped, yet the old image of hunter-gatherers living permanently at the edge of starvation is also too simple. Ethnographic comparisons show that famine has not been equally frequent in all foraging societies, and some warm-climate hunter-gatherers have experienced less famine than many agricultural populations. These living groups are not replicas of Paleolithic communities, but they remind us that mobility, food sharing, broad knowledge, and dietary variety could provide protection against the failure of a single resource. Prehistoric diets also differed greatly between places. Some northern groups relied heavily on large animals and aquatic foods because edible plants were seasonally limited. Elsewhere, wild plants could provide a substantial share of nourishment. Isotopic and dental evidence from sites such as Taferelt in North Africa has shown that plant foods could be much more important than older hunting-centered pictures suggested. The survival value of a varied diet was not only in calories. Different foods supplied protein, fat, carbohydrates, minerals, and other nutrients needed for growth, reproduction, immune function, and tissue repair. Still, archaeology cannot reconstruct every meal. Animal bones often preserve more visibly than plants, while many leaves, fruits, and underground foods disappear without trace. Burned seeds, microscopic residues, dental calculus, tooth wear, and stable isotopes can recover parts of the diet, but each method sees only part of the past. This incomplete record has sometimes made prehistoric meals appear more dominated by meat than they truly were. For human longevity, the important pattern is variation rather than one universal menu. Food could support a body for decades when knowledge, access, sharing, and environmental conditions remained favorable often enough. The same body could be shortened by repeated childhood stress, nutrient deficiency, tooth damage, infection, or a sequence of lean seasons. Storage and food processing could reduce some seasonal risks in certain times and places, but these practices were not uniform and did not make supply dependable everywhere. The prehistoric world offered periods of plenty, ordinary adequacy, and scarcity, sometimes within the same year. Long life depended partly on passing through all three, without a temporary shortage becoming an irreversible decline. Knowledge held by experienced adults may also have helped groups recognize lean seasons early and shift effort before conditions became severe. Food did not determine an exact age of death. It quietly altered the margin between recovery and failure, season after season, until those small differences accumulated across a human life. The prehistoric human body was shaped by movement, but movement was never the same in every landscape or every season. Some communities traveled frequently between water, plants, animals, stone sources, and temporary camps. Others remained near productive rivers, lakes, or coasts for longer periods before moving again. Distance alone does not describe the full physical demand. People also crossed uneven ground, climbed slopes, walked through mud or snow, carried children, transported food, gathered fuel, and moved tools or materials that could not be left behind. These activities strengthened muscles and placed repeated loads on bones and joints. Regular activity could support endurance and bone strength, but the same work could also contribute to pain, wear, and injury. When loads were heavy, recovery was limited, or movement continued through illness. The skeleton can sometimes preserve the long-term effects of physical activity. The shape and internal structure of limb bones respond partly to mechanical loading, while joints may show degeneration after years of movement or repeated stress. Areas where muscles and tendons attach to bone can also change, although researchers cannot look at one mark and identify one exact occupation. Age, body size, disease, genetics, and many different activities may produce similar skeletal features. A strong or heavily developed bone does not prove that a person performed one particular task, just as arthritis does not prove that prehistoric work alone caused the damage. The body records accumulated experience, but it does not preserve a written list of daily actions. Climate changed the cost of those actions. In cold conditions, the body had to protect its core temperature while continuing to move and find food. Shivering and other forms of heat production required energy, so inadequate clothing, shelter, fire, or nutrition could narrow the margin of safety. Wetness and wind could make moderate cold more dangerous by increasing heat loss. Hands and feet could become less effective, making tool use and travel harder before exposure became fatal. Yet cold environments should not be imagined as permanent scenes of helpless suffering. Humans used fire, animal skins, shelter, planning, and detailed knowledge of local conditions to reduce exposure. Bodies could also become partly accustomed to repeated cold, although physiological adaptation had limits and differed among individuals. Heat created a different strain. Movement under high temperatures increased the need to lose heat through sweating, making dependable water important. Dehydration could reduce physical performance and become dangerous, especially during long travel or illness. Shade, timing, rest, and knowledge of water sources could reduce the burden, but a delayed return, an injured companion, or an unusually dry season could transform familiar movement into a serious threat. Physical strain, therefore, came from the relationship between work and circumstance, not from activity alone. The same journey could be manageable after rest and food, but exhausting during hunger, pregnancy, recovery from infection, or advanced age. A healed injury might alter the way weight was carried, slowly placing additional stress on other joints. Tooth loss could weaken nutrition, which could then reduce the body's ability to repair tissue after demanding travel. The effects accumulated quietly. One long walk rarely determined lifespan, but years of movement, repeated minor injuries, limited recovery, and changing weather could gradually reduce the body's reserve. At the same time, remaining active may have helped many adults preserve strength and practical independence far into later life. Prehistoric movement was neither a simple source of health nor a sentence of early physical destruction. It could build the very endurance needed for survival, while also exposing the body to the conditions that wore it down. When we ask how long prehistoric humans could live, we are asking how long a body could continue balancing those two outcomes, adapting to repeated effort while still retaining enough strength to recover from the next difficult season. Fire, shelter, clothing, and knowledge of the landscape did not remove the dangers of prehistoric life, but they could reduce them one by one. A fire could warm a resting place, dry damp materials, provide light, discourage some animals, and make certain foods easier to chew or digest. A shelter could block wind, rain, or direct sun. Clothing and wrapped animal skins could create a warmer layer of air close to the body. None of these advantages guaranteed survival, yet each could preserve energy that the body would otherwise spend staying warm, recovering from exposure, or struggling to process food. Over a single night, the difference might seem small. Repeated across many seasons, it could help determine whether a weakened child, an injured adult, or an older person survived long enough to recover. The archaeological evidence for these behaviors is uneven. Fire leaves burned bone, charcoal, heated sediment, and clusters of material around hearths, but natural fires can produce some similar traces. Researchers therefore examine context before deciding that a fire was controlled by humans. Clear hearth evidence extends back hundreds of thousands of years, while claims for much earlier controlled fire remain debated. Shelters are even harder to identify because wood, hide, grass, and other organic materials usually decay. Post holes, arranged stones, concentrated activity areas, or repeated occupation beneath rock overhangs may suggest shelter, but they rarely preserve the complete structure. Clothing is more elusive still. Skins and plant fibers usually disappear, so researchers often infer their use from hide-working tools, bone needles, traces of fibers, or the ability of humans to occupy cold regions. This means we should not imagine every prehistoric group equipped in the same way. Technologies appeared at different times, and people adapted them to local needs. A cave could provide useful protection in one landscape, while elsewhere people may have built light structures or used natural windbreaks. Fire could be maintained regularly by one group and used less consistently by another. For the question of prehistoric longevity, these differences mattered because the body's biological potential could only be reached when enough daily risks were controlled often enough. A person did not need perfect protection. Small reductions in cold stress, foodborne danger, nighttime exposure, or physical exhaustion could preserve the strength needed to survive the next illness or injury. Knowledge made these tools effective. Fire required fuel, dry material, attention, and the ability to keep it from spreading or dying. Shelter required choosing ground that would not flood, collapse, or expose its occupants to wind. Clothing had to be obtained, shaped, repaired, and kept usable. People also needed to remember water sources, seasonal routes, animal movements, edible plants, and places where stone or wood could be found. Such knowledge could turn a landscape that appeared empty to an outsider into a network of reliable possibilities. It could also fail when climate changed, resources shifted, or a group entered unfamiliar country. These advantages therefore remained conditional. A hearth could burn out, smoke could irritate lungs and eyes. Shelters could gather waste, insects, or pathogens if occupied repeatedly. Fire could cause burns, and cooked food could still spoil. Protection from cold did not prevent infection, childbirth complications, tooth loss, or violent injury. Technology changed probabilities rather than abolishing mortality. Its greatest effect may have been cumulative and quiet. A warmer night saved energy. A softer meal allowed someone with worn teeth to eat. A sheltered recovery period gave a fracture time to stabilize. A remembered water source prevented a dangerous delay. Each success added no dramatic number of years by itself, but together they could create the conditions in which a human body capable of decades was allowed to continue. When asking how long prehistoric people could really live, we should therefore look not only for extraordinary survivors, but also for the ordinary protections that repeatedly kept ordinary dangers from becoming fatal. No prehistoric human survived an entire lifetime through individual strength alone. Every person began as an infant who could not walk, find food, maintain warmth, or escape danger without help. Even after childhood, independence was never complete. Adults depended on knowledge learned from others, tools made through shared traditions, and resources that could vary unpredictably from one day or season to the next. A skilled forager might return with more food than one household could eat, while another capable adult might return with nothing because animals moved, plants failed, or illness reduced the day's work. Sharing could spread those uncertain outcomes across several people. It did not guarantee that everyone received an equal portion, and it was probably shaped by kinship, friendship, obligation, reputation, and local custom. Yet when food moved between individuals, one person's temporary failure did not always become immediate hunger. That small protection could matter greatly to lifespan. A body recovering from fever or injury needed energy even when it could not produce food at its usual level. A pregnant or nursing woman faced demands that changed across the year. Children required nourishment long before they could reliably obtain enough for themselves. Older adults might contribute knowledge or lighter work while needing help with more demanding tasks. In each case, survival depended partly on whether the group could absorb a temporary imbalance between what a person needed and what that person could provide. Childcare reveals the same pattern. Human children develop slowly and remain dependent for many years. Mothers were central, but studies of recent hunter-gatherers show that fathers, grandparents, siblings, and unrelated companions may also hold, watch, feed, or protect children. These communities are not direct models of deep prehistory, and the amount of shared care varies widely. Still, human childhood would have been difficult to sustain if every mother had always carried the entire burden alone. Additional caregivers could allow a mother to gather food, rest, recover from illness, or care for another child. Their help did not merely make life more comfortable. Under demanding conditions, it may have altered whether both mother and child remained alive. Cooperation also appeared in quieter daily tasks. Knowledge itself could be shared across generations, where water remained in a dry season, which foods required careful preparation, how weather changed along a route, or how to avoid repeating an old accident. A younger person did not have to discover every danger alone before learning to survive it. A fire required fuel and attention. A shelter needed repair. Water had to be found, food processed, children watched, and signs of danger noticed. Several people could distribute these demands so that illness, fatigue, or age in one member did not stop every essential task. The same principle applied after injury. A person with a fractured leg or severe wound might be unable to travel or gather food for a period. Healed skeletons show that some individuals lived long enough for serious damage to repair, but bone alone cannot tell us precisely how much assistance they received. Some may have remained partly mobile and adapted their work. Others probably needed food, protection, or time that companions helped provide. Care should therefore be treated as a possibility supported by the severity and duration of impairment, not as a sentimental certainty attached to every healed wound. Nor should cooperation be romanticized. Prehistoric groups could experience tension, exclusion, competition, and violence. Resources sometimes became too limited to support everyone fully. Relationships could fail, and help may have been distributed unequally. What matters for the question of longevity is not the idea that ancient communities were perfectly kind. It is that human survival was organized through interdependence. Food sharing, childcare, teaching, firekeeping, and assistance during weakness reduced certain risks often enough for some lives to continue. A long prehistoric life was carried by one body, but that body had first been fed, protected, instructed, and repeatedly given time by other people. An older adult in prehistory did not need to be the strongest person in the group to remain useful. Physical speed could decline, joints could become painful, and worn teeth might make some foods harder to eat. Yet many forms of knowledge became more valuable precisely because they required time to accumulate. A person who had lived through many seasonal cycles could remember which valley held water during a dry year, when certain plants usually appeared, where animals crossed after heavy rain, or which route became dangerous when rivers rose. Such knowledge was not abstract. It could influence where a group moved, when it waited, what it carried, and how it responded when familiar conditions began to change. One remembered detail might not extend a life by many years, but repeated decisions based on experience could reduce risk for several people at once. Older adults may also have carried technical knowledge. Tool making, hide preparation, food processing, fire maintenance, and the recognition of usable stone or wood often required careful observation and repeated practice. A younger person could learn by watching, imitating, and being corrected before a mistake became costly. Archaeology rarely preserves the act of teaching itself, but the continuity of complex techniques across generations implies that knowledge had to move from one person to another. Older individuals were not the only teachers, and age did not automatically produce skill, yet a longer life created more opportunities to refine and transmit what had been learned. Social memory may have mattered just as much as environmental knowledge. In small communities, relationships with neighboring groups could influence access to marriage partners, exchange, shelter, information, or support during shortage. An older person might remember past alliances, conflicts, kin connections, or obligations that younger members had not witnessed. That memory could help prevent a misunderstanding or reopen a relationship after a period of separation. We cannot know how often such roles existed, because social ties rarely leave direct marks on bone. Still, human groups survive not only through food and tools, but through remembered relationships. Later life may therefore have held value in ways that are almost invisible archaeologically. This does not mean every older adult was respected, wise, or protected. Age could bring disability, isolation, dependence, or reduced influence. Groups under severe pressure may have been unable to support someone who needed extensive care. Older people could also make mistakes, lose memory, or hold knowledge that no longer matched a changing environment. The idea of the universally honored elder is as misleading as the idea that older people were simply burdens. Their position probably depended on health, personality, relationships, local custom, and what the community needed at a particular time. For the question of prehistoric longevity, the quiet value of older adults creates an important possibility. If later life offered useful knowledge, care, memory, or coordination, then surviving beyond peak physical strength could still benefit others. Those benefits may have encouraged food sharing and protection, but they should not be turned into a simple evolutionary bargain in which help was given only in exchange for usefulness. Human care also grows from attachment, familiarity, and obligation. An older person may have been helped because of what they knew, because of what they had previously given, or simply because they belonged. Their continued presence could preserve knowledge that would otherwise disappear with one death. Each additional year could hold another winter remembered, another route mapped in the mind, another technique passed to a child, or another relationship kept alive. The value of older adults was therefore often cumulative rather than dramatic. It rested in information that could not be replaced quickly and in social bonds that had taken decades to form. A long prehistoric life may have mattered not only because one body endured, but because time stored itself inside that person and remained available to everyone around them. Older adulthood becomes easier to see in the human fossil record during the Upper Paleolithic, especially among early modern humans in Europe. This does not mean that old age suddenly appeared at one moment, or that earlier humans were biologically unable to live for many decades. Individual Neanderthals and earlier members of the human family had already survived into later adulthood. The change identified by researchers concerns frequency. In one influential study, Rachel Kaspari and Sang-Hee Lee compared the proportion of older and younger adults in dental samples from several successive periods of human evolution. They used the eruption of the third molar as a marker of adulthood and classified as older those individuals whose dental wear suggested an age more than twice the age of that eruption. This was not the same as calling someone 60 or 70 in modern terms. It was a relative method designed to compare survival across fossil groups when exact ages could not be established. Their results suggested a gradual rise in adult survival through time, followed by a much larger increase among early Upper Paleolithic Homo sapiens. In that sample, older adults outnumbered younger adults for the first time in their comparison. The pattern was striking because it implied that more people were living long enough to occupy a later generational position within the group. A population with more older adults could preserve more experience, support more children, and maintain knowledge across longer spans of time. It may also have been able to grow more quickly, because surviving adults could continue contributing food, care, skills, and social connections. Yet, the result must be handled carefully. The study did not reconstruct a complete population census. Fossils come from scattered sites, formed under different conditions, and the people who entered the archaeological record were not a random sample of everyone who lived. Burial customs changed. Preservation differed between caves, open sites, soils, and climates. Some periods are represented by more remains than others. Tooth wear also depends on diet, food preparation, grit, and cultural practices. Not only on chronological age, researchers attempted to reduce these problems by making comparisons within a consistent framework, but no fossil ratio can escape every source of bias. The label older adult also refers to a threshold based on dental maturity, not to a precise age familiar from modern life. A person placed in the older group may have been in what we would call middle adulthood rather than extreme old age. The study therefore supports an increase in survival beyond early adulthood. It does not prove that large numbers of Upper Paleolithic people routinely reach 70. Later research on late Pleistocene mortality has also emphasized demographic instability and low adult survival in many samples. Different methods, regions, and time periods do not always produce one simple upward line. The emergence of more visible older adults should therefore be understood as a broad pattern, not a universal transformation experienced by every community at the same time. Even with these limits, the pattern matters. Earlier sections of this story have shown that the human body was capable of long adult life before the Upper Paleolithic. What may have changed was the number of people who were allowed by their environment, technology, social organization, and accumulated knowledge to approach that capacity. Better clothing, shelter, food processing, exchange networks, and cooperation may all have contributed, although the evidence cannot assign the change to one cause. A growing presence of older adults could then strengthen the same cultural systems that supported survival, creating a relationship in which longevity and accumulated knowledge reinforced one another. Older age became more visible not because danger disappeared, but because more lives crossed enough dangers to leave later adulthood as a recognizable part of the population. The fossil record still blurs their exact years, yet it begins to show something important. In some Upper Paleolithic groups, growing old was no longer only an unusual individual possibility, it was becoming a more noticeable feature of human society. The beginning of agriculture is often imagined as the moment when human life became safer. Fields could be planted, animals could be managed, and food could be gathered into stores rather than searched for each day. In some places, farming did increase the amount of energy available to a community and made it possible for more people to live within the same landscape. Yet a larger food supply did not automatically mean a healthier body or a longer individual life. The transition was gradual, occurred independently in different regions, and produced different results. But many early farming populations show a difficult biological paradox. They could support growing numbers, while many individuals carried signs of poorer health. One reason was that dependable calories could come from a narrower range of foods. A community relying heavily on a few cultivated grains might obtain enough energy while receiving less dietary variety than people who combined many wild plants, animals, fish, and seasonal resources. Concentration also changed the meaning of failure. When one crop supplied much of the year's food, drought, pests, flood, or an unsuccessful harvest could affect many households at the same time. Storage could protect against a short interruption, but stored food could spoil, be consumed too early, or become insufficient when several poor seasons followed one another. The change was never identical everywhere, and hunter-gatherer diets were not always balanced or abundant. Still, dependence on carbohydrate-rich staples could increase tooth decay and sometimes leave shortages of particular nutrients. Teeth preserve this shift clearly in many archaeological populations. Cavities often became more frequent when sticky or finely processed plant carbohydrates formed a larger part of daily food. A painful or infected tooth was more than an inconvenience in a world without modern dentistry. It could reduce the foods a person was able to chew, weaken nutrition, and in severe cases allow infection to spread. The bodies of some early farmers also show reduced average stature or signs that growth was interrupted during childhood. Short stature alone does not prove poor health because height is influenced by ancestry and many environmental factors. When changes in stature appear together with dental disease, skeletal stress, and evidence of infection, however, they can suggest that children were growing under heavier biological pressure. Settlement added another layer. Living near fields and stored food reduced some demands of movement, but it brought people, waste, and sometimes domesticated animals into closer and more repeated contact. Water and soil near a settlement could become contaminated. Parasites and infections could circulate among more hosts, while permanent buildings and food stores attracted insects and rodents. Not every disease associated with later cities appeared immediately with the first farmers, and many older claims about diseases jumping directly from livestock to humans have been revised. The broader principle remains sound. Denser and more settled populations created different opportunities for pathogens than small, mobile groups did. Farming work could also be demanding. Preparing soil, harvesting, grinding grain, carrying water, and tending animals repeated particular movements across years. These tasks could support strong and active bodies, but they could also concentrate wear in joints, backs, and teeth. None of these changes means agriculture was simply a mistake. Cultivation could buffer some seasonal shortages, produce stores, support children, and allow communities to grow. Over time, farmers developed new crops, food processing methods, exchange networks, and ways of managing local disease. Health patterns could improve or worsen within the same settlement across different generations. The lesson for prehistoric longevity is therefore not that foragers always lived longer or that farmers always died younger. It is that the ability to feed more people must be separated from the condition of each person being fed. A population could expand, while childhood stress, dental disease, infection, and physical strain shortened many individual lives. More food changed the scale of human society, but it did not guarantee that a single human body would be allowed more years. Settlement changed more than the distance people traveled. It changed how often the same bodies, animals, waste, water, and soil came into contact. A mobile group could leave behind refuse, human waste, and contaminated ground when it moved. A permanent or repeatedly occupied village had to continue living beside the byproducts of its own survival. Food scraps accumulated, water sources could be used by many households, animals might be kept close to homes or brought through shared spaces. Floors, storage areas, and paths were reused year after year. None of these conditions guaranteed disease, but together they created new opportunities for parasites and microbes to circulate. The important change was not simply that farming people became unclean, it was that larger numbers of people remained close enough for infections to find new hosts more easily and for contamination to be renewed faster than the environment could remove it. Some infections spread through water or food. Others passed through breath, touch, insects, or contact with animals and their waste. Breath, intestinal disease could be especially dangerous to infants and weakened adults because repeated diarrhea removed water and nutrients from the body. Parasites might not kill quickly, yet they could reduce growth, worsen anemia, and make recovery from another illness more difficult. In a settled community, such burdens could return again and again. The consequences for lifespan were often cumulative rather than dramatic. A child who survived several infections might still grow more slowly. An adult weakened by chronic disease could become less able to work, heal a wound, or endure a poor harvest. A brief illness that would have passed under better conditions could become fatal when combined with malnutrition, pregnancy, age, or physical strain. Close contact with domesticated animals also changed disease possibilities, but this part of the story requires caution. It is often said that farming immediately produced most human infectious diseases by transferring them from livestock. Ancient DNA has made that picture more complicated. Some pathogens have histories older than agriculture, while others appear to have expanded, changed hosts, or become more visible only after populations grew and movement between settlements increased. Direct genomic evidence has now identified brucellosis in a pastoral community about 8,000 years ago, showing that at least some animal-associated infections were present in early farming worlds. Yet one confirmed pathogen cannot represent every village or every period. Disease transitions unfolded unevenly across regions and over thousands of years. Population size also mattered. An infection that creates lasting immunity may disappear from a very small group after passing through everyone who is susceptible. Larger settlements, linked villages, migration, and exchange could provide enough new hosts for transmission to continue or return. This did not mean that every Neolithic settlement experienced constant epidemics. Many infections were local, seasonal, or sporadic. Some communities may have managed waste and water more effectively than others. Houses could be rebuilt, activity areas separated, animals kept at varying distances, and settlements abandoned when conditions became difficult. Human behavior continued adapting to the risks it had helped create. Archaeological evidence from places such as Çatalhöyük shows that health pressures changed through the long life of a settlement rather than remaining fixed. As population density increased, skeletal evidence suggests heavier exposure to infection and demanding labor, but later changes in organization also altered these patterns. Settlement was therefore not a single biological disaster. It was a new disease environment that offered benefits and costs at the same time. Stored food, shared labor, and stable shelter could protect life during some seasons, while crowding, contamination, and repeated exposure could shorten it in others. For prehistoric longevity, the result was another separation between population success and individual survival. A village could grow, reproduce, and endure for centuries, even while many of its inhabitants carried disease burdens that reduced the number of years each body could reach. Population growth does not tell us how long the average individual lived. A farming community could become larger even if adults did not survive to greater ages, because population size is shaped by births as well as deaths. If women began having children at slightly younger ages, if the interval between births became shorter, or if more children survived long enough to reproduce, the number of people could rise while disease, dental problems, nutritional stress, and physical strain remained common. This is the central distinction behind the Neolithic demographic transition. Agriculture allowed more people to be supported on the same area of land, but the first demographic advantage of farming may have come more from increased fertility than from a dramatic extension of adult life. A village full of children could be a sign of rapid growth, even when relatively few people reached advanced age. Archaeologists have tried to identify this change through cemeteries, settlement numbers, radiocarbon dates, and the ages represented among human remains. One frequently used clue is the proportion of children and adolescents within burial populations. When many young individuals appear relative to adults, the pattern may indicate that many babies had recently been born, creating a larger generation of children. Yet this evidence is difficult to interpret. A high number of child burials might reflect high fertility, high childhood mortality, special burial practices, or some combination of all three. Infants may also be buried in different places or preserve less well than adults. No cemetery can be treated as a perfect census. Researchers therefore compare several kinds of evidence and look for broad patterns rather than reading population growth directly from one burial ground. Across many regions, the arrival or intensification of agriculture is associated with periods of demographic expansion. More predictable staple foods, stored harvests, and reduced mobility may have made it possible for mothers to wean children earlier or carry the energetic cost of pregnancies spaced more closely together. These explanations are plausible and supported by demographic models, but they were not identical everywhere. Farming systems varied, and so did women's workloads, diets, breastfeeding practices, disease exposure, and access to help. A change that increased fertility in one community might not have produced the same result in another. Growth also did not continue smoothly. Archaeological records from parts of Europe and North America show regional booms, followed by stagnation or decline, harvest failure, conflict, soil depletion, epidemic disease, climate variation, migration, and social disruption could all affect the number of settlements and people, although it is rarely possible to assign every collapse to one cause. The spread of agriculture was therefore not a simple upward path toward larger and healthier populations. It created systems capable of rapid expansion, but those systems could also become vulnerable when many people depended on the same crops, water sources, and social arrangements. This distinction changes the way we answer the central question of prehistoric lifespan. A population can succeed biologically without giving each member a long life. If each generation produces enough surviving children, total numbers can grow even while many adults die before later adulthood and many children never reach maturity. Conversely, a small, slowly growing community might contain individuals who live for many decades. Population size, fertility, mortality, and longevity are connected, but they are not interchangeable. Agriculture eventually supported towns, cities, and vast human populations, yet that achievement should not be projected backward as immediate evidence that the first farmers lived longer than the foragers before them. In many places, growth came through more births and denser settlement before it came through safer childhoods or extended old age. The fields increased the number of human lives that could begin. They did not necessarily increase the number of years each life was allowed to continue. That difference is quiet, but it prevents the success of a population from being mistaken for the survival of a person. The question, how long could prehistoric humans live, appears to ask for one number, but it actually contains three different questions. The first asks about life expectancy at birth. This measure begins with every newborn and includes every death that follows. whether it occurs after a few days, during childhood, in early adulthood, or many decades later. In populations where infant and child mortality was high, life expectancy at birth could remain low even when a noticeable minority of adults survived much longer. It describes the mortality conditions surrounding an entire generation from its first moment. It does not tell us the age at which most adults were expected to collapse, and it does not place an invisible limit on anyone who had already survived the dangers of childhood. The second question asks about remaining life expectancy after a person has reached a particular age. A child who survived to 10, an adolescent who reached 15, and an adult who reached 30 no longer faced the same set of probabilities that existed at birth. The deaths that had already removed many younger people still affected the population's original average, but they no longer belonged to the survivors' future. From each new age, the calculation began again, using only the dangers that remained ahead. This conditional measure comes closer to the experience of an actual adult. It asks how much longer a person might live after crossing one or more of the most dangerous stages, yet even this answer is an average, not a promise. Injury, infection, childbirth, food shortage, environmental change, and social support could make the paths of two adults sharply different. The third question concerns the longest lives that were biologically and socially possible. This is not the same as the age most people reached, nor the age an average adult could expect. It concerns the smaller number of individuals who survived repeated hazards and entered later adulthood. Their existence matters because it reveals that the human body was capable of continuing beyond the young ages suggested by life expectancy at birth. But exceptional survivors must not be turned into representatives of everyone. One older skeleton can demonstrate possibility without demonstrating frequency. The fossil record makes all three questions harder to separate. Infant remains are easily lost, adult ages become increasingly difficult to estimate, and many bodies never entered conditions that preserved them. Older adults are often placed into broad categories rather than assigned exact ages. A skeleton described as older than 50 may belong to someone only slightly beyond that threshold, or to someone who lived considerably longer. The evidence, therefore, does not produce a clean table showing the age of every prehistoric person. It gives ranges, proportions, and incomplete signs of survival. Comparisons with recent hunter-gatherer populations can help researchers understand how low life expectancy at birth can coexist with substantial adult longevity. Those communities, however, have their own histories and cannot be used as direct copies of Paleolithic populations. They illustrate demographic possibilities rather than supplying exact prehistoric numbers. The three answers must therefore remain separate. Life expectancy at birth tells us how severely early mortality affected a whole population. Remaining life expectancy tells us how the outlook changed after a person survived to a later stage. Exceptional longevity tells us how far some human lives could extend when enough dangers were avoided. Confusing these measures created the familiar claim that prehistoric humans simply died at 30. Separating them does not yet give us the final number, but it reveals what any honest answer must contain. We are no longer asking for one age, shared by everyone across the enormous and changing span of prehistory. We are asking how survival changed from birth to adulthood, how often later life appeared, and how far the longest lives may have continued beyond the average. Only after keeping these measures apart can the evidence begin to answer the title without creating another misleading certainty. The closest honest answer is that prehistoric humans could live far longer than the famous average of 30 years, but the chance of reaching those later decades was uneven and often small. For many prehistoric populations, life expectancy at birth was probably low because so many deaths occurred during infancy and childhood. Comparisons with recent hunter-gatherer populations often produce values in the 20s or 30s, but these figures cannot be transferred directly into the Paleolithic past. They show only how a low average can exist in a naturally long-lived human species. Once childhood was survived, the possible lifespan changed. A teenager who reached adulthood had already passed through one of the most dangerous parts of life and could potentially live for several more decades. Reaching the 40s was therefore not a biological surprise. Reaching the 50s was also possible, and some individuals clearly lived long enough to accumulate severe tooth wear, healed injuries, joint degeneration, and other signs of later adulthood. The evidence becomes less precise when we ask whether people reached 60, 70, or beyond. Bones do not preserve exact birthdays, and older adults are often assigned to wide categories, such as 45 or older, or 50 and above. A skeleton placed in one of these categories may have belonged to someone just beyond the threshold, or someone who lived much longer. This means that the upper end of prehistoric lifespan is blurred by the methods used to estimate it. It would be too confident to announce that prehistoric people commonly lived to 70. It would also be too confident to claim that no one ever did. Studies of living foraging and small-scale subsistence populations show that when people survive childhood, adult deaths often cluster much later than the average at birth suggests, sometimes around the late 60s or early 70s. These societies have medicine, histories, contacts, and disease environments different from those of deep prehistory, so they cannot supply a direct answer. They do demonstrate that the human body does not require industrial life in order to remain alive into later decades. Fossil evidence provides a more limited view. Neanderthals such as Shanidar once survived into substantial adulthood despite serious impairment, while La Chapelle-aux-Saints one reached an older stage marked by tooth loss and degenerative disease. Early, modern human samples from the Upper Paleolithic also contain a higher proportion of adults who survived beyond early adulthood than earlier fossil samples. None of these findings creates an exact maximum age, but together they show that later life was real. The safest range is therefore layered. Many lives ended before adulthood. Many adults probably died during their 20s, 30s, or 40s from infection, injury, childbirth, scarcity, exposure, and violence. A smaller number reached their 50s. Some prehistoric Homo sapiens probably entered their 60s, and rare individuals may have lived longer, especially in communities where food sharing, shelter, accumulated knowledge, and social support reduced repeated dangers. The pattern would have differed between species, regions, and periods. A mobile Ice Age group, a warm climate coastal community, and a later farming settlement did not face the same mortality pressures. Even neighboring communities could experience different outcomes after drought, epidemic disease, conflict, or several unusually favorable years. Whether anyone in deep prehistory reached the exceptional ages known today cannot be demonstrated from the surviving record. The answer depends on what we mean by could. If we mean the average life from birth, the number was often low. If we mean the years available to someone who had already survived childhood, several additional decades were possible. If we mean the furthest limit reached by rare individuals, the evidence becomes too uncertain to provide a final number. Prehistoric humans were not built to die at 30. They possessed the biological capacity for later life, but only some were allowed by circumstance to approach it. A long life before written history was more than the survival of one body for an unusual number of years. It represented a chain of dangers that had been crossed repeatedly. The person had survived the helplessness of infancy, the infections and shortages of childhood, the uncertainty of adolescence, and the injuries, illnesses, and physical demands of adult life. No single moment explains such survival. It was built from many ordinary moments in which food was found, warmth was maintained, wounds remained clean enough to heal, and other people continued to provide help when strength temporarily failed. The final age recorded in bone was therefore only the visible end of a much longer process. It could not reveal every winter endured, every illness resisted, or every quiet act of assistance that allowed another season to begin. This is why prehistoric longevity should not be reduced to a contest between the past and the present. Modern people usually live longer because sanitation, vaccination, antibiotics, surgery, safer childbirth, stable food systems, and public health have prevented many early deaths. These improvements are real and should not be minimized. Yet, they did not transform a naturally short-lived animal into a long-lived one. They allowed more members of an already long-lived species to approach the later years their bodies had always been capable of reaching. Prehistoric humans shared that biological capacity, but they lived in conditions where one treatable infection, difficult birth, damaged tooth, or failed season could remove decades that might otherwise have followed. Those who reached later adulthood were not proof that prehistoric life was healthy or easy. They were proof that its dangers were sometimes survived. Their presence also changed the communities around them. An older person could remember conditions that occurred too rarely for younger adults to have experienced them. A route used during an earlier drought, a method of preparing a difficult food, or the memory of a neighboring group could become useful again after many years. Older adults could assist with children, repair tools, maintain social connections, and teach skills that had taken decades to refine. They could also experience pain, disability, dependence, and loss. Later life was not automatically wise, powerful, or comfortable. It was simply a stage of human existence that carried both limitations and possibilities. The educational lesson is not that ancient people secretly lived as long as people do today. Most did not. Nor is it that everyone died near 30. That belief confuses an average shaped by early mortality with the lifespan of every adult. The more accurate lesson is that human longevity has always been conditional. Biology created the possibility of a long life. Environment, chance, technology, nutrition, and relationships determined how often that possibility was reached. This understanding changes how we read numbers in the present as well as in the past. An average can describe a population without describing the fate of any one person. A maximum age can prove what is possible without revealing what is common. A skeleton can preserve survival while leaving the surrounding life mostly silent. Honest history must keep those differences visible rather than replacing uncertainty with a simple answer. The prehistoric record cannot tell us the oldest age ever reached by a human before writing. It cannot recover every child who disappeared from the archaeological record or assign an exact birthday to every older skeleton. What it can show is that later adulthood existed, that some damaged bodies continued, and that human lives were prolonged not by strength alone but by repeated adaptation and interdependence. Behind every unusually old prehistoric individual stood a body capable of repair, a landscape that remained survivable, and perhaps other people who made weakness temporary rather than fatal. How much of a long human life came from the strength of the body, and how much came from the presence of other people?